So thanks everyone for coming today. I really appreciate the fact that everybody can be here in this virtual format. We are really happy to have you all here for the kickoff of our JCDREAM Symposium series. We're going to be doing this once a month here for a little while. And while I know that JCDREAM is probably familiar to many of you, I think that we actually have a bit of a national audience today, thanks to our keynote speaker, Tom Gradell. And so I wanted to give a brief overview of JCDREAM and tell you a little bit about what we're all about. So JCDREAM is a Washington State Research Institute. The acronym stands for the Joint Center for Deployment and Research in Earth Abundant Materials. It's a heck of a mouthful, but it's a nod to replacing critical materials in the energy sector with earth abundant solutions. And so when we look back to the guidance that we received from the founding legislation that enacted JCDREAM back in 2015, it talks a lot about clean energy. It talks about transportation and addressing those two spaces with sustainable and earth abundant materials, as well as recycling, to make sure that these are both sectors that can thrive in the future. So I'll explain more about earth abundant materials and critical materials, as will Tom. But for a minute, I want to focus about what energy and transportation means in Washington State. So transportation especially is a little bit different in Washington State. It's a little bit less about passenger vehicles and a little bit more focus on things like aviation, marine industry, and shipping. And of course, this is a bit of a nod to our local industries. Of course, we have Boeing and the entire aviation and aerospace supply chain here in the Northwest. We have PACCAR, one of the largest medium and long haul truck manufacturers in the world. The marine industry is thriving. And of course, Amazon Logistics has also become a major player in the shipping industry. The other thing that's important to focus on is the fact that Washington State is the cloud computing capital of the world, with the presence of both Microsoft and Amazon here. We have a very strong presence from Google and Facebook. And so there's a very strong presence in the data economy in Washington State. And of course, this industry is using more and more energy as it grows. In fact, it's actually bigger than commercial aviation at this point in terms of energy consumption. So with that in mind, I'd like to walk you through a vision of how we can power this fantastic economy in Washington State on clean energy. And then I'll get into some of the material implications of that later on. So first, let's start with energy. So in Washington State, the energy sector looks much like it does in the rest of the world. We've got an electric power grid. We've got a liquid fuels infrastructure that is, it's gasoline for automobiles, diesel, jet fuel, and marine fuels. And then we also have a natural gas infrastructure, which of course powers all of our, stationary and residential and industrial sector. So what's exciting though about Washington State is where we are and where we're going. So this is a picture, of course, of where we want to head. We want our energy, our power grid to be 100% renewables, hydroelectric, and basically we want to decarbonize the electric grid. So right now it's actually a long ways down that path. We've got a handful of fossil fuels and nuclear power sources on the grid, and we've got liquid fuels, of course, in the orange circle, and we've got the natural gas sector in the green circle. But with a little bit of additional energy storage, I think there's a very strong chance that we can pretty much eliminate those from Washington State's power grid. The other thing that we want to do eventually is take all of that clean and zero carbon power and use it to power our transportation sector, and then our industrial and residential and data sector as well. And again, we are making fantastic strides in that space. So there's been a strong deployment of clean electric vehicle deployment in the passenger vehicle space. And like I was saying, we've got a fantastic burgeoning aviation sector. And then the other thing, we've got a lot of electric trucks running around. PACCAR has been working on producing light duty and medium duty trucks. Amazon is deploying a lot of these vehicles from PACCAR and other manufacturers. The marine industry is actually starting to flourish in an all electric sector with electric ferries and electric tugboats. And so this is all really very exciting news. The other thing is that our industry, residential, and data sector is actually largely powered by clean and green electricity. So that's fantastic. The tricky thing is, as we look at where our current infrastructure is powered, we are still heavily reliant on these liquid and gas fuels. So this is something that's actually going to be very difficult to get away from as we think about it. So I think if you point to aerospace as a specific example, it is highly unlikely that we're ever going to fly an airplane across the Pacific Ocean on a battery electric system. It's probably just not, it may not be possible. And so that's a classic example of where we're really going to need liquid fuels. You see the same thing when we talk to truck manufacturers about what they're able to do with electric trucking. It's applicable for short, for short trips, but as soon as you start doing long haul trucking with high utilization of those assets, you really need liquid fuels. We see the same with ocean going vessels and many other modes of transportation. The other thing is that our natural gas infrastructure is currently powering huge portions of our industry, housing, and data economy, and it offers great stability both on a seasonal level and from a day-to-day perspective. So the trouble with this, though, of course, is that all of these fuels, the use of these fuels is emitting carbon dioxide. And so I think we are all familiar with the trouble associated with CO2 emissions. And so what we want to be doing is trying to capture those CO2 emissions in some way. So you can do this in stationary situations pretty easily. You can also do it in certain transportation applications, or you can actually capture CO2 from the atmosphere as needed. The interesting thing as we start to do that, and we're just at the very beginnings of that CO2 capture process, is now you actually have a chemical feedstock. So the carbon in that CO2, if we are able to combine it with hydrogen, which we can generate by splitting water from clean, renewable electricity, we now have the necessary feedstocks, both carbon and hydrogen, to remanufacture fuels. So you can, on the orange loop over there, you could make kerosene, diesel, you could make methanol to power trucks, ethanol, formic acid, any number of different things that could power the liquid fuels economy. You also can produce methane or butane or propane, and perhaps even inject hydrogen directly into the natural gas infrastructure. So now you have an opportunity to have a completely closed loop where our CO2 emissions are essentially zero, and we're powering this entire economy on that foundation of clean, renewable energy combined with energy storage. So this is a fantastic vision. We're really excited to consider this. It is a ways off. We're going to be at this for decades, I expect, trying to get to this clean energy future. And along that way, one of the things that I want to highlight that we're going to start to run into is our critical materials issues. So if you look at those sectors, and we take a look at the periodic table, which of course I'm guessing everybody here is familiar with, there are some problem spots. And so in this periodic table down here in the lower left-hand corner, what I've done is highlighted the energy critical materials. So these are a subset of the periodic table where we have supply issues, human rights problems, or geopolitical issues in the supply chain of accessing those elements that we need for this economy. So a few examples. I think most notable probably is cobalt. Cobalt is in all of our lithium-ion batteries. I'm sad to say that everyone's cell phone has a little bit of cobalt that was mined in the Democratic Republic of the Congo by children digging holes in the ground. And Apple and Samsung have all admitted this. It's kind of a known thing. But it's just one example of a trouble spot. So cobalt, the DRC has about 2/3 or 70% of the cobalt in the world. And then that supply runs through China and into your cell phones, laptops, and electric vehicles. Another example is the rare earth elements. Of course, we've heard a lot about rare earth elements in things like the China trade wars. And the trouble is that one example, neodymium and dysprosium are used in permanent magnets, which then go into electric vehicle motors, and wind turbines. Another one that you probably haven't paid too much attention to yet is these catalysts that are part of that electrofuels economy that we're aiming for. So if you want to split water into hydrogen and oxygen, you're going to need platinum group elements. So they're shown in blue there on the periodic table, and they're things like platinum, ruthenium, and iridium. And then even converting CO2 and hydrogen into fuels to create that liquid fuels economy, again, requires platinum group elements. So these are all the critical materials that we need to focus on, making sure that that is a stable supply, that these are low cost, and really the focus needs to be on finding earth abundant alternatives. So there's been a ton of activity here in Washington State. JCDREAM has been bringing together all kinds of folks from all over the state to work on solving some of these challenges. And I'll give you a few real brief examples. So Professor Yohei Lin at WSU has come up with a nickel and iron based catalyst. So nickel and iron, of course, are some of the most earth abundant elements on the planet. And he can replace an iridium catalyst with actually better performance in splitting water in electrolyzer technologies. So that's pretty exciting. At the UW, the Clean Energy Institute has deployed some JCDREAM equipment to actually replace the indium, which is used in the transparent ITO conductor on the surface of a solar cell. They've been able to print a copper grid to replace that indium tin oxide layer with copper. Copper is also not the most abundant, but it's a heck of a lot more abundant than indium. So this kind of repeats itself over and over again. We're working on creating the infrastructure and collaborations that are going to make this future a possibility. And so real briefly, I want to talk a little bit about where JCDREAM is headed and pitch the next symposium. So we're going to be starting the next symposium in November with a focus on electrofuels and catalysts. We'll have speakers from WSU. Professor Jean-Sabin McEwen is going to be speaking, as well as Steve Ciotti from PACCAR. Then the following month in December, we're going to launch an educational arm of JCDREAM called Materials Washington, where we're going to be gathering educators, community college sector, and high school instructors to try to launch this organization around creating the curriculum and building the workforce so that we can create this economy down the road successfully with a knowledgeable workforce. In January, we're going to address Washington policy with State Representative Norma Smith, who I like to say is the founder of JCDREAM, and Lisa Brown, the director of the Commerce Department of Washington State. In February, we'll dive into battery materials. And then also probably in February and January, we'll launch our next round of seed grants. So the seed grants is what's been stimulating all of the research and interest from the previous slide, all the different partners that have gotten involved. A lot of those folks have been involved through our seed grant program, which we've done. This will be the 4th year in a row that we've done the seed grant program to help get people started. So I invite everyone to apply and get involved in that. And then of course, a really big important part of this is the industry collaborations. JCDREAM really wants to focus on aligning academic researchers at our fantastic research institutions with folks like the National Lab and Pacific Northwest National Lab and all of the fantastic industry that we have here in Washington State, both the big players and small startup companies. So we're looking forward to bringing everybody together in this way. And with that, I will let everyone head off to a breakout session so we can talk a little bit about this and try to figure out what's next. Thanks. So thanks, everyone. It's my great pleasure to introduce today Professor Tom Gradel, Professor Emeritus from the Industrial Ecology and Chemical Engineering Department at Yale University. Professor Gradel has dedicated his career to studying, publishing, and speaking in the field of critical materials and their link to climate change and industrial ecology. He was elected to the U.S. National Academy of Engineering for outstanding contributions to the theory and practice of industrial ecology in 2002. His textbooks are staples in the critical materials courses, and his current interests include the flows of materials within industrial ecosystems and the development of analytical tools to assess the environmental characteristics of products, processes, the service industry, and urban infrastructure. Professor Gradel is a Pacific Northwest native from Portland, Oregon, and he was named the Regents Distinguished Alumnus of Washington State University in 2019. And while it pains me as a UW alum to say this, go Cougs. And with that, I give you Tom Gradel.
Thank you very much, Aaron, and welcome everybody. What I'd like to do today is to talk with you about critical materials, which has been a topic for several years, but I'd like to put a little bit more spin on it by relating it more directly to its use in modern technology, modern industry. So a few pictures of modern technology just to get us into the mood. And my point here is that whether you're in marine technology, green energy technologies, almost any technology, it's very likely that you're using materials that somebody or other has designated as critical. And I want to spend first some time to talk about the designation of critical materials and some of their properties, and then to relate them a little bit more to some of the concerns or some of the relationships when they're used with modern technology. So the critical materials part. There are four colors or lack thereof on this chart. Of course, it's a picture of the periodic table, everybody's favorite diagram. And we have a number of elements, about 9 here, that are colored in yellow. Those are elements that the US government has designated as critical for the United States. We have a few that are blue. Those are elements that the European Union has designated as critical to the EU, but the US has not designated them as critical for the US. Elements in white here, nobody regards them as critical. But the largest of the colors is obviously elements in red, and those are elements that both the United States and the European Union that developed extensive research in the past few years on how to designate materials. Anything in red there is critical to both the EU, the US, and probably other countries that haven't put out such a comprehensive public documentation of where they stand on this. Now, what makes materials critical? One is certainly where the supplies come from and whether you need to import them at all. This is from a US Geological Survey chart, which on the left shows the different commodities. In the middle is an estimate of the percentage of those commodities used in the United States that are import reliant. And on the right are the countries that are the major import sources. So you see, first of all, that there's more than 20 different commodities for which the United States is almost entirely reliant on imports if our manufacturing activities are going to be using them. The other thing to point out is that for some of these elements, cesium, for example, which comes from Canada, we're not too worried about materials being accessible from Canada. But others, Aaron mentioned the rare earths earlier, coming from China, we're entirely dependent on other countries for those materials. Another factor of interest in the critical materials area is that most elements are not mined for themselves. Most elements come as byproducts from the major materials shown in this diagram in blue. For example, in the lower left, you see copper as the host element, the one that's mined for, and it is very commonly the repository for small amounts of arsenic, selenium, rhenium, tellurium. Zinc toward the upper right is the host metal for indium, cadmium, germanium, and so forth. In my research group at Yale, we've tried to look at this in some detail, what we call the companionality of the different materials. And on this version of the periodic table, the coloration reflects the degree to which elements are used as companions. Anything in red here, by our best estimate, is used entirely as a byproduct of major metals. Anything in blue is mined directly for itself, and there are a few, such as silver, the gold box in the center right. We have silver mines, and some silver comes from there, but the majority comes as a byproduct of copper and other metals. It's also interesting to say, well, if we don't have good access from getting materials as imports or mines, why don't we substitute something for it? A few years ago, our group tried to look at that question. We found the major uses for the elements, typically 5 or 6 major uses, and we evaluated whether there were adequate substitutes for each of the uses. What we did on this diagram is to score the metals on whether they could be basically whether they had good substitutes. Anything in on the diagram that is red means there are no suitable substitutes for any of its principal uses. Anything in blue says there's a substitute for all the principal uses, and the colors in between represent shades of those two extremes. And you see there are a number of materials such as magnesium, the red block in the upper left, manganese in the first wide row of the periodic table, and so forth, that essentially have no substitutes at all. Usually when I show this diagram in the classroom, somebody inevitably says there's no blue on the diagram. And in our estimation, there are no elements for which there is a suitable substitute for all uses. So there are some for every element for which there are no substitutes, and for some, there aren't substitutes for any of their uses. So this says we need them all given today's technology. One more periodic table here to look at, and this is the end-of-life recycling rates for the metals. And this was done by getting together in 1911, really getting together everybody in 1910, and saying, and these were experts from industry and the academic world and government, to say, what are the recycling rates for metals? difficult to be too quantitative here because by and large, there aren't any regulations any place that make public statistics on recycling. But we did the best estimation we could. And then we divided the metals into 5 groups. Anything in blue on this diagram, the group assessed as having recycling at rates of better than 50%. This is end-of-life recycling when materials and the products in which they're used come out of service. There are a few elements that are somewhere in between, and anything in red here is elements for which the group believed there was essentially no recycling at all going on. So in those cases, and that's obviously the most abundant color on this diagram, in those cases, we have to get everything by mining because we're just using it once, which doesn't sound very sustainable. A little deeper look at the recycling perspective here. And again, going back to our flower garden of metals. And again, let me start with copper at the lower left. Copper is the host metal for rhenium, Re, and unless you happen to have a molybdenum mine that has some rhenium in it, this is the route to rhenium. At the top, not extreme right, but the top center right is zinc, and there is the host metal for indium next to it. If we look again at the issue with rhenium, almost all of it is used to make turbine blades for jet engines. A turbine blade is a single crystal device. It's about the size of your hand. It's single crystal, very challenging to manufacture, very valuable, and everyone gets an individual number. When they need to be replaced or when the engine comes out of service, because of their value and because everybody knows where they are and because there aren't very many corporations that own them, most of them get back into reuse. Something over 80% of all turbine blades and their rhenium goes around for reuse. If we look at almost any screen we see these days, this is the Space Shuttle Atlantis, we have LCD displays all over, and as Aaron said earlier, those screens have a surface layer of indium tin oxide. Typical screen has maybe a gram or a few grams of indium. They're very challenging to recycle, and as a result, we don't see too much of that indium coming back. So to go back to our end-of-life recycling chart, on the top horizontal row, copper and zinc toward the center right, both with good recycling statistics. And at the lower left of center, rhenium, also with good recycling statistics because of this close link to reuse of the turbine blades. If we look at just to the lower right of zinc, however, we see that indium has almost no recycling. So we're using indium once, we're throwing it away, and we get it maybe if zinc is mined and if that material is processed. Another thing that's interesting to explore in the critical materials area is the topic of alloys and economics. Critical materials have always been specified from the start, and that dates back now to a decade or two. They've always been specified on the basis of pure materials, but many of them have most of their use in various alloy forms. And so far, that hasn't been part of the discussion to any degree. Our Yale group a few years ago attempted to say, can we specify the fraction of each element that sees use in alloy form? And this is our attempt to do that. The blue on the diagram says, here's an element that is mostly not used in alloy form. Red says almost always used in alloy form, and the other colors fall in between. So in the center at the wide row, top of the diagram, iron, virtually always used as an alloy. Alloy steels, carbon steel, stainless steel, so forth. Next to it, we see cobalt, that's been mentioned earlier, and something like 60% on average used in alloy form of various kinds. If we take a look at that from the global perspective, this is an estimate made by an industrial corporation in 2019 that about half of the materials used globally, of cobalt's use globally, is for batteries, and that's the dark blue half of the diagram on the left. Another 15% or so, the next darkest diagram around toward the bottom right, used in superalloys, and then we have a few other diagrams that are not not used in alloy form, such as pigments. Depending on your business, if you're in the lithium-ion battery business, there's a lot of cobalt used in a lithium-ion battery. Cobalt sees other uses. It's used, a particular alloy of 14% cobalt in the lower left here is used in landing gear, although you could do that with other alloys, but this is a particularly suitable one. And as I mentioned earlier, cobalt is used in aircraft superalloy blades at concentrations of 10 or 15%. So one could ask yourself, if cobalt becomes in short supply, which are the industries that will be willing to pay more for it? Well, there's different ways to make batteries. Maybe you'd like to use cobalt, but you can do something other without it. You need to make landing gear, but you have different alloys available there that could be used. But you can't make a modern turbofan engine, really, without using a lot of cobalt. So cobalt and the industry that uses it as one of its central materials is likely to set the price. So if things get in short supply and you're in the lithium-ion battery business, this could be difficult for you because the aerospace industry is very likely to be the dominant factor here. We can look again at this for vanadium. All the little stars on this diagram are uses of vanadium in alloy form, and vanadium is used something like 95% as an alloy, the various alloys. High strength steel, the 60% part of the wedge on the right side here is the most common of the alloy forms for vanadium. but there are many others. This diagram from Boeing, materials in the 787. And what I've circled here is that we have an aluminum, steel, titanium materials fraction that's in yellow. These are the brackets that hold up the engines, connect the engines to the wings. And it says titanium there, but the actual material titanium is usually used on in aircraft is an alloy of titanium, 6 vanadium, 4 vanadium, 6 aluminum. And again, we're in a situation where we have vanadium used in various industries. It's used in all the tool steels, or most of them, where its concentrations are 1.5 to 2%. Widely used in high-strength, low-alloy steels at quite low concentrations, but important for those applications. And pretty widely used in aircraft fuselage use, where titanium, aluminum, vanadium alloy is the common material. And again, it's likely that aerospace will set the price point here. So if you're in other businesses, but you need vanadium, you need to be aware of that. It's useful to look at composite materials, which are increasingly entering into the manufacturing world. And let me look at lightweight core materials used increasingly in aerospace and automotive applications. And this plot for a number of possible materials in this area has density as the abscissa, gravimetric energy as the ordinate, and the ideal is something of low density, high gravimetric energy, namely the yellow wedge in the upper left corner, which is largely titanium 6-4, again, the vanadium material. Honeycomb panels typically have the honeycomb in the center, some adhesive film that connects the honeycomb to backing sheets and front sheets on the outside. And these show up where you wouldn't necessarily anticipate it if you weren't an aircraft or other transport designer. And one place that it's definitely being used is in the marine ferry services and other marine vessels around the Seattle area and elsewhere. The honeycomb material has in it magnesium, which you may remember is a critical material, designated critical material. And the hull is an aluminum alloy that also contains almost 5% magnesium. So there's a fair amount of critical material riding in the Kitsap ferry, which I'm informed has now gone into service around the harbor areas of Seattle and surrounding regions. The uses of magnesium, almost 2/3 for transportation and some other random uses. So in the transportation business, anybody in that business is to some degree or other a competitor for magnesium, one of the critical materials. What I've been talking about is the current state of affairs as best they can be specified for critical materials and for where they're used. It's also interesting, though, and important to look at what might happen over time. because we don't design things with the idea of using them for a year or two and then throwing everything away and starting all over. You'd like a design to be stable in a material sense for a fair number of years, maybe quite a few years going forward. And this is done with scenario studies, where we don't know what the future is going to look like, but we can tell stories about what it might look like. And telling those stories and thinking about the results helps us think more deeply about where things might be going in the future. We've been doing scenario studies for critical materials and other materials at Yale for some years, and I want to show you a little bit of what we have there. This is a scenario study for copper demand, and we used 4 scenarios to study this issue. On this diagram, we used actual data for copper demand from 1980 up to 2010. And at that point, we invoked 4 scenarios. One shown in green here, we call the security foremost scenario, where we envision a world where most everybody hates everybody else. International shipping is down. Security is high, and because of those restrictions, we see copper demand increasing significantly, but less than in the other scenarios. We have 2 scenarios, market world in orange and toward resilience in blue, that are variations on business as usual. And you see on the diagram that going forward in time, we project significantly more copper demand. Finally, we did a scenario that we call equitability world, shown in purple. And that is a world in which all peoples on the planet have a reasonably decent lifestyle. In order to enable that, it takes a lot more material. And so that comes up quite a bit higher than any of the others. In all cases, we're talking about at least a doubling of demand and perhaps a tripling or more in the case of equitability world. If we look now at the supply side of the house, the red line here is a study from Australia, where the Australians studied every copper mine in the world, how big it was, how fast it was going to be developed. And what they anticipated from that study was that the copper supply would continue to increase until about 2030, 2035, and then start to decrease as the mines producing the bulk of the copper started to run to lower grade ores and exhaust significant portions of what they had. So their study, not yet refuted, it's now 5 or 6 years old, I think, says that past 2030, 2040, we need to rely on recycled supplies or secondary supplies. And the dashed lines in the bottom center of the diagram show the recycling supply for copper predicted in the scenarios. So if we add the red line and the dashed lines, a typical curve will look like the dark green trajectory in the top center of the diagram. But we also plot the total demand that we anticipate from our scenarios, the last slide I showed, and you see that that's above the predicted total copper supply. Now, these are stories. They're not definitive in any way, but they're there to help us think, to help us say, suppose the Australians are right, suppose the scenarios are reasonable. We need to think about this in some detail. We did these studies for 7 different metals. Here we have them on a diagram with the time scale on the bottom, the cumulative demand as a percentage of total demand on the vertical scale. And the unit here is what we call resources to mid-century, the amount of resources of each metal that we think might be available during that period. This is a sloppy number. Nobody knows it very well. So we've purposely given it big error bars and put a big gray swatch across the diagram. And for some of the metals, the ones on the low side, manganese, aluminum, iron, perhaps nickel, the scenarios suggest no challenges for supply out to mid-century at any rate. Copper looks like it's just about at the boundary, so we should be thinking a bit hard about copper. Lead, if we continue to use it in lead-acid batteries, depending on how fast the transition to renewables goes in the transportation sector and other allied sectors, we may have an issue with lead. It certainly looks as if we should take careful looks at zinc, which appears to be far above the estimated materials availability at mid-century. I want to make a few final remarks on this material and get out of the way a little bit to enable you to ask questions. But first, I've tried to show you there are many definitions of criticality. There are criticality specifications by governments, but you can define this in various ways in terms of how much is in alloy form rather than elemental form, how much is recycled typically, how much is used as a companion in the mine and processed in that way, and so forth. The use of metals in alloy form pretty obviously plays important roles in criticality. Some alloys are recycled very effectively, as with the superalloys in aircraft engines. Some are recycled very poorly, and this really hasn't been part of the criticality discussion, at least overtly. Third, all metals have a single use or a set of uses that tend to set the price point. This is the economic discussion. If you are using a critical material, you obviously know what you're paying for it, but you probably need to know who your competitors are for that metal, who may be in some completely different industrial sector, but who might have the potential to argue with you economically about getting a metal that's in short supply. Finally, we have the scenarios issue. Metal demand scenarios are important in thinking about some of these issues. And at least the ones that we have done, and I think the ones that 2 or 3 other research groups around the world have done, suggest that criticality needs to think hard about the global development paths that could be followed. And if you see that a particular one is going to be followed, that might be also something for you to think of, especially if you're building products that you hope to be in production and in use for a few decades, 1, 2, maybe even 3 decades. That's when there is at least some possibility of materials demand exceeding materials supply and causing disruptions that might or might not be predictable. This is not to say that this issue is all gloom and doom. It is to say that one should exercise some caution in thinking about critical materials, and that being informed about them is vital, I think, to modern day industrial use of metals of all kinds, materials of all kinds. And I'm looking forward to what questions you have as we move on to the next part of this program.
I'll start out. I actually was thinking along the same lines as Suresh Bhaskaran, who was in my chat session, about wanting to hear from Tom about his perspective from industry, because JCDREAM really focuses a lot on trying to align critical materials issues with the industry perspective. So Suresh, if you don't mind, why don't you go ahead and ask Tom your question and we'll take it from there.
Tom, hi. It's been a few years since we were on the advisory board of CMI, and a great talk and great perspective, great information. Both Aaron and I were really trying to better understand how industry, especially the large industries that make a lot of products and they depend on all these materials from a number of different sources, how do they go about reducing their risk? Lining up their supply chain, distributing the manufacturing in a number of different countries. And so it would be good for us to understand, maybe not for all the different materials, but overall, in terms of how do you triangulate that with the kinds of policies and research that the government must undertake and state organizations should also undertake?
I think that's an interesting challenge, in part because businesses, for all the reasons one could guess, are a little bit close-mouthed about how they address these things. They're, for sure, one thing that many businesses, large ones anyway, do is they will enter into contracts, long-term contracts with specific mines or specific mining companies, and take part of what they have coming out of the mine. When the auto industry started using catalytic converters, General Motors went to South Africa and contracted for, I think, 1/3 of the output of at least one of the platinum mines there. So that's certainly one way to do it. Another way is to try to use industry cooperative pressure to make materials available. But it's easier to do that with major metals than it is with trace metals, because trace metals don't have a public auction opportunity. They aren't on the London Metal Exchange. They're really sold under the counter officially, but still invisibly pretty much. So one can provide general guidelines as to how to go about this by saying something like, try to get long-term relationships with suppliers, try to distribute your suppliers. These aren't new ideas for anybody, I suppose, but they're maybe a little bit more sensitive here. But I think industries in various ways are playing this in all kinds of different approaches. If one of your materials happens to be recoverable and recyclable, try to up the recycling and then process it. I know Aaron, I think, said to me a little bit earlier, well, how do you how do you get vanadium out of an alloy once you've recycled it? And once you've recycled the alloy, and the typical response there is, once you've made the alloy, you never want to demake the alloy. It's very energy intensive. Nobody knows really how to do it efficiently. What you do is try to keep that alloy in service, and that means that ideally, instead of having 56 different aluminum alloys in your manufacturing process, you try to see what you can do with, say, a dozen. And so minimize the diversity of the materials you're dealing with. That would be another way to approach things.
Thank you.
We had a question from Sarah Jane. Sarah Jane, do you want to ask your question?
Sure. Hi, everybody. Hi, Tom. I just was wondering about the limitations on some of the primary metals that you showed, like limitations on zinc and lead supply, for example, and what your sort of thoughts are about what that's going to do to supply of byproduct minerals, byproduct elements.
Yeah, reasonable questions. I think the key there goes to how fast the world is going to develop and how the world is going to develop. If the world decides to make life better for everyone, this means moving a lot more electricity from one place to another. It means decent buildings. It means good public transportation. All these things take materials. And I think if we get the sort of world in the next few decades that tries to make for equitable lifestyles, it will put enormous pressure on materials demand. If things don't go quite as dramatically, then I think as we get more efficient with recycling metals in various forms, alloys in various forms, and inevitably technology will think of something new, so that might go either better or not so good for the materials sustainability business. So part of it is we don't know. It's good to have possible futures in mind. If we get a material like zinc, to pick the obvious example from the talk, that turns out to be in shorter supply, then we need to look carefully at the companion metals and say, are these companions to any other major hosts? In some cases, you do have 2 or 3 hosts that will produce companions, the same companion. But if there aren't, then we really have to look carefully at what we're doing with the companions as well as with the host, because we may run into sort of a group supply challenge as opposed to just an individual metal challenge.
Thanks.
Thank you both. I didn't see, is Jason Selowitz still here? I'm trying to keep track of who's been able to stick around or not. You there, Jason?
Yeah, I'm still here.
Go for it.
So I had one question and then another question built off of what Scott Beckman put in the chat. So I'd like to see the answer.
Yeah, that's great. Thank you.
Yeah, one question is about graphene, and if there's anybody here that's working or knowledgeable about direct air capture and of carbon and the potential to generate graphene from that, and the use of graphene in energy storage devices.
Not a topic I know much about. Clearly, there's potential there for some real interesting developments in energy mobility, energy transport. But I think it's going to be a couple of decades before we see wide range rollout of graphene in any way that has a major impact on supply. We will see, though, but there's technology always has a way of adding something you didn't think of. But I think even though I think the US at least has said graphene could be a critical material, nobody quite knows how to wrap their arms around that yet because the uses aren't so obvious in any major, dramatic, high volume way. So this is open for you to become a hero, I think.
One thing I could comment on, Jason, having spent a good chunk of my career in the carbon space, is that there are a lot of forms of useful forms of carbon, and there's a lot of really pretty good ways to utilize waste feedstock material. I think carbon is soot, right? So you can essentially, you can pyrolyze, you can partly combust various feedstock materials. You can hydrogenate those. There's a variety of different things that can be done to keep carbon in that circular chain and actually produce carbon products as a bit of a carbon sequestration approach. You won't probably sequester as much carbon as we need to, but you can certainly get it back into a solid form that's usable in all kinds of things, batteries and structures and all sorts of different kinds of applications. So that's definitely a possibility. And I would look to carbon black, graphene, activated carbons, all kinds of different carbon materials that can be that carbon sink. And then I think Scott Beckman, as you alluded to, has left, but his question is to ask, and I think Jason, you were going to ask about, can we develop a critical metals recycling industry in Washington? And then related, Scott's question was, how well is the US situated in the recycling industry, and are we recycling critical metals in the US, or is it being performed offshore? So I think just kind of a general question about how we establish a domestic critical materials recycling system in the United States, and to what extent that exists right now.
The perception of our group at Yale, particularly Barbara Reck, one of my colleagues, is that Europe is thinking well ahead of the US on the recycling business in general. It's always been difficult to evaluate recycling, partly because nobody requires you to keep recycling statistics. And so the only way to get a handle on it of any kind is to get a bunch of people, label them experts, and put them in a room and say, what do you think? And that's where the United Nations study came from. It's interesting that it's 10 years old now, and there's been nothing that has supplemented it. It's still probably largely correct, I would think, but there's no way to verify that because the statistics are not routinely available to us in the US, in Europe, anyplace else. And because designers have not thought much at all about how to make materials that are readily remanufacturable, readily reusable, readily recyclable, there's not much of a track record in any of these areas on how to go forward with it, even though we know that some industries like Xerox with the copiers and Caterpillar with some of its big machinery are doing a fair amount of this, but those are individual corporate statistics, generally not publicly available, although we know there is some expertise in specific pockets of U.S. industry. I don't think there is much expertise in doing it generally. I think it is a potential opening for something that could be really valuable were it to center itself in the Northwest in an industry non-specific way, and try to get some traction on the general area of how to do a better, more responsible job of using things more than once.
Our next session is with Steve Ciotti of PACCAR and Jean-Sabin McEwen from WSU. It will be on e-fuels and electric catalysts for the decarbonization of heavy-duty transportation. We also have a session scheduled for December 8th with Mel Cassette and Ann Avery, where we will be talking about advancing critical, rare, and abundant materials education in Washington State. And then in January and February, we will have some more sessions scheduled for you as well. So stay tuned. Thank you so much all for being here, and we'll see you next time.
Thanks, everyone. Have a good day.